Hello and welcome back to the course on machine learning. I hope you enjoyed the previous tutorials and now you're quite confident with the upper confidence bound and the Thompson sampling algorithm, or at least the intuition behind them. And today we're going to quickly compare the two because they do solve the same problem. They solve the problem of the multi-armed bandit, and let's have a look at some of the pros and cons of each of the algorithms. So of course there's lots and lots of different advantages and disadvantages and differences between the two, but we'll just highlight the main ones. So here we've got the two algorithms. On the left we've got the UCB and the image from the intuition tutorial that will help us kind of remember what it's about, and the Thompson sampling algorithm, and same the image behind it. So the first characteristic is probably that is different is that the UCB is a deterministic algorithm, and actually there's lots of different modifications to the UCB algorithm. You can find them online. There's lots of different white papers on how the UCB algorithm can be modified to improve it and to make it better at one thing, or like adds one advantage, maybe makes it a bit better result, but it makes it more computationally intensive, or the other way around, and so on. So, but all of those algorithms belong to a family of UCB algorithms, or upper confident bound algorithms, which are all deterministic. And basically, what that means is that it is very straightforward, right? So once you have at certain round, it's very straightforward what's going to happen. You just look at the upper confidence bound, and whichever one has the highest, that's the one you pick. You pull the algorithm, yes. You pull the lever, yes. Then you do get like a random value from the machine, but that's on the side of the machine. So that randomness is on the side of the machine, and then whatever value you get, it is very determined. It is very deterministic what the UCB is going to do with that value, so all of the steps that the UCB actually takes, they're very deterministic. There's no randomness in the algorithm itself. Whereas on the other hand, the Thompson sampling algorithm is a probabilistic algorithm, because in the algorithm itself, it has these distributions which represent our perception of the world and where we think the actual expected returns of each of those machines might lie. And therefore, every time we are implementing or iterating in the Thompson sampling algorithm, we actually generate random values from those distributions. So if you rerun a round in the UCB algorithm, just one given round, after you've received the value from the previous value from the machine, and then you rerun the round, it's always going to be the same result. Whereas in the Thompson sampling algorithm, after you've received the previous value from the machine and you rerun the current round, it's always going to be different, because you're always sampling from your distributions which characterize your perception of the world. And that is a whole different type of algorithm. It's a probabilistic algorithm. And those two things, they actually have a few different implications, right? So for instance, one important one is that the UCB requires an update at every round, right? So basically the value that you get back from the machine, so once you've pulled the lever and you get a value back from that machine, that value you have to incorporate it right away in order to proceed to the next round. You cannot proceed to the next round until you have incorporated that value, until you have made an adjustment to the algorithm based on that value. Because if you don't make the adjustment, then nothing changes and you're going to be stuck. Whereas in the Thompson sampling, it can accommodate delayed feedback. And this is very important. This basically means that if you pull the lever and you only will get the result, or you will only know the result of pulling the lever 500 rounds down the track, right? Not right away. You'll only get to know the result 500 rounds later. The Thompson sampling algorithm will still work. Why will it still work? Because if you now run the algorithm without even updating your perception of the world, you're still going to get a new set of hypothetical bandits, right? You're going to generate a new expected return for every bandit, because you are generating them in a probabilistic manner. And this is very important to understand, because This gives the Thompson sampling that advantage that you don't have to update the algorithm with the result every time. And in terms of bandits, of course, that doesn't really matter that much, because if you're playing in the casino and or if some hypothetical person is playing in the casino and they're pulling these levers, they get to see the results right away, so they could update the algorithm. But in terms of websites and ads, that is a big deal, right? So not even just displaying ads on a website, or you could use this for like A/B testing instead of A/B testing the different layouts of your website, right? You could use a Thompson sampling algorithm to have that balance between exploitation and exploration right away. So basically, anything you're doing on the web with Thompson sampling, or like solving a multi-arm bandit problem for your business or for a business on the web, you're getting all these thousands and tens of thousands of clicks, right? And to update the algorithm right away, that would be very highly computationally costly, or it might require additional resources and a complex process. Whereas what the Thompson sampling algorithm allows you to do is to update your data set or your information algorithm in a batch manner. So you wait until you get 500 clicks, or you wait until you get 5,000 clicks, you update the algorithm, then you let it run, and then it runs, and then you get another 5,000 clicks, and then you update the algorithm again, and it will still work. And that's a very important thing, that flexibility that the Thompson sampling algorithm creates. And finally, again, we're not going to go into too much detail on the pros and cons, but the Thompson sampling algorithm is actually, it has better empirical evidence than the UCB. And you'll find this phrase, better empirical evidence, and that's because up until recently, the theory behind the Thompson sampling algorithm, or the whole research wasn't complete. It's only been researched in a lot of detail just a few years ago, and now you can find like a lot of information on the Thompson sampling algorithm. But previously, people just see that from experimental evidence, the Thompson sampling algorithm does work better than the UCB, and that's exactly what we're going to see. Spoiler alert, that's exactly what we're going to see in the practical tutorials for this section. So we're going to be now coding Hadlan will walk you through coding the same exercise, the same problem that we had previously with the UCB. Now you're going to be solving it with the Thompson sampling algorithm, and you will see actually some very interesting results. We'll leave it at that. And I hope you enjoyed these intuition tutorials, and off we go to the practical side of things. Can't wait for you to get started. Hadlan will show you all around, and I'll see you back here next time. Until then, enjoy machine learning.